Hello and welcome to another fun time with 2D and 3M friends. Hope all you cool cats and kittens are ready for some induction and things. Good morning, Tammy, and good morning to everyone else. Does somebody want to say some words, just so I know I'm not talking to the void? It's like my...
Good morning.
Who said this? I must know.
Muhammad.
Nice to meet you, Muhammad. Thank you. Okay, so where shall we start today? So you do have a midterm coming up. I would like to remind you of that. I have specifically so the benefits of having two classes happening side by side, our class and the other class. The benefits of that is when one of the instructors gets too excited and wants to do stuff, the other instructor can say, calm down. And likewise, I can also say that to Wolfram. So the midterm was going to be a bit harder next week, and we talked and we're like, let's not make it hard. Let's remember you guys were asking for some. You gave us some useful feedback. So in particular, one of your feedback was assignments are too long. So this assignment 3, you'll notice instead of asking you to prove a bunch of stuff, we just put it there for fun. We're not going to ask you to prove it. We're not going to make it an exercise or a homework or anything. It's just here's some fun stuff, we might test you on some of this, right? It's not clear. We don't know, but we thought, hey, let's just show you some other stuff. This actual assignment had more things involved. It didn't stop here. But anyhow, I just want to let you know that we really are listening to your feedback and we're not trying to make your lives too hard. Sometimes we get a bit too excited. That's all. And honestly, we do need you to tell us when things are sufficiently hard. So that's why we're getting the TAs to make the. You're welcome, Shrill. So we also, if you look at the contents, you'll notice we also put some selected solutions. In case some of you aren't aware, there is some selected solutions with explanatory prose. So that was released, I think, last week. So right here at the very bottom, if you see selected solutions, so there's you can go in there and hopefully we'll release another one this week. Hopefully we'll try to get out one every week for you, and we have all the solutions. The reason they take a while is why we're the point is to explain what's going on, right? What did you try, some gotchas, right? Stuff like that. And in the same vein, we just made a recent Teams channel for tips and study strategies. So after lecture last time, a student had an aha moment. They're like, this finally makes sense. And hopefully that student will share their aha moment and how they saw things before and how they will see things in the future. And perhaps students sharing their the way they see things is easier for other students than the way I would communicate it to you. So that's why I made that channel for you. And of course, we're leaving the prose from the TAs. We're not going to edit it. So this is how your TA Naseem decided to show you the solution, and she wrote a bunch of nice stuff. And other TAs might give you other solutions, right? So in her exposition, Naseem also decided at one point, hey, I've showed you how to do these things. Here's some hints on how to solve this problem now. So just some stuff for you to read and practice, to explain all this text, to explain a small proof, right? To try to help out. So please let us know how useful or not that may be. Assignment 3 does have some stuff that's for midterm 4. So I do want to just point that out right now. So if you look into it, there's some stuff here. Stuff specifically related to midterm 4 is down here. Okay, so we just want to let you know. I don't think I'll make a midterm prep. I think last time I made one, it was too long. So I think that's what I tried to do with the assignment. I just put in a little bit for the midterm, right here. Also, if you pay attention, you'll notice some theorems, like many of the theorems, are repeated multiple times in this notebook. Point isn't time, but in order to go a bit slower, and some of the theorems are literally almost copy. And I even tell you, hey, this is copy pasted. You can prove it by copy pasting, or I'm trying to really try to get you to understand some stuff. So sometimes I even say, hey, do some stuff to try to help you to understand. So it might look a bit long, just like homework 13 did the other day, but it's a lot of text and exposition and examples. So there's a lot of worked out examples in here. So I hope this will be helpful for you. Okay, ducks. So maybe we'll stop talking about that. If there's anything else you want to talk about, please let me know. And we'll continue with induction. So you saw homework 13 the other day, and that was just using the word using, which you're all familiar with. Everyone's been using the word using for a while now. This was an important feature for midterm 3. So using is not new. And you've all met induction, which was the key characteristic of midterm 2. So using and induction are not new. And so that's why we gave you homework 13. It was, we're trying to be slow, and we're not trying to go fast. So we're like, hey, let's just remind them of these two things they're using in preparation for today's lecture. So today's lecture is going to be on induction and using for other data types besides the natural numbers. Okay, and we're not going to get too complex. We're just going to go just a step up. Instead of the next possible thing right after numbers is called lists. It's a really small tweak to the data type. So we'll look at that today. Are there any questions, concerns, or queries before we continue? I don't know what the main topic is for midterm 4 because I have not finished writing it. I will probably have to take stuff out so as not to be too long. I'm really worried about length. Don't want to be too long for you guys. I'll try to have it done soonish and I'll announce, hopefully. The slides will be posted on Avenue after lecture. Okay, ducks. There was a homework released already today. There may not be a homework prep. Mentioned that earlier. Okay, ducks. So let's talk a little bit about the theory of induction before we get to actually using induction for lists, which is the next up from natural numbers. So the reason we care about induction and primarily in computer science is because induction lets us prove that loops terminate, that the loops are not going to keep going on forever and ever, right? So to show that the loop is terminating, you find a value that the loop changes, and then you say, hey, this value gets smaller and smaller each time the loop runs. And for the if your value happens to be a natural number, you know that the natural numbers eventually stop. If you start at the value being 100, eventually it's going to get smaller and smaller until it reaches 0. Okay, so eventually it stops. But if your value is an integer, and you know that integer is always going to get smaller and smaller, then it might never stop, and so your loop might never stop. So that's why we care about induction in particular from this angle. So a way to organize induction is to say, hey, you know what? I care about these sequences of smaller and smaller numbers. Can I ever have an infinite descending chain? Can I have smaller and smaller numbers forever and forever? The natural numbers say no, you can't do that. Other numbers say yes. So this one says yes. This one says no. This is the positives. At one point they stop, or do they? How many numbers are there between 0 and 1? Right? There's 0.5, and then there's 0.51 and 0.522. So let's talk about what it means to do induction in this setting. Okay, ducks. We're going to use this symbol, which you can read as before or predecessor of or part of or simpler. The book uses this symbol as well, It's very similar to the order relation, less than or equal to, or square less than or equal to, but it doesn't have to be an order. It's just a relation. We're just talking about an arbitrary relationship. Okay, so that's why we're not going to use less than in particular, and we're not going to be using square than. Okay, so we're just talking about an arbitrary relation, and we'll get to relations in general in the few coming weeks. Okay, C is the complex numbers. So the complex numbers can be thought of as a plane and like a big sheet of paper, and there's no real, there's no complete ordering for them. Okay, there's no standard ordering for them. Okay, please continue to ask questions. So the idea for induction, and we've tried to communicate this before, is that to show that a property holds over some structure, you say, all right, let me show that it holds for the simplest possible structure, okay? And then there's ways to make new pieces of the structure, some construction C, and let me say, if it already holds for X, and then I use X to make a new value, then the slightly complicated value is still going to be true, okay? So we say, you know what, the structure at the simplest case is already satisfying P, and if you have something that satisfies P, then additional constructions for the structure satisfy P. So for example, 0 satisfies the property, and successor, which is a way to make new numbers, satisfies the property. Okay, so that's the idea of construction of induction. It just says, hey, if you have this complicated thing and you want to know if this complicated thing satisfies a property, well, if each construction preserves the property, then you can pop off the constructions and look at the simpler pieces. Eventually, you'll get to the simplest possible piece, which is the base case. And if you showed that the simplest possible pieces satisfy the property, and you know the constructors preserve the property, then when you tack on the constructions, it continues to be true. Okay. So here's an example. Suppose I want to prove every stack of books in my home is green. Every stack of books in my home is green. So the way to do that would be like, okay, well, the stack of books is a structure. How do you make elements of the structure? Well, you start off with an empty stack. There's nothing here. Okay. That's one way to make a stack of books. It's empty. Another way to make a stack of books is to take a book, specifically take a green book and put it on top of an existing stack. Okay. So now, if we want to show that every book in my stack is going to be green, I just need to check the 2 ways to make stacks of books. The empty stack, well, there's no books in here, so they're all green. All 0 books are green. Great. Suppose I have an existing stack. Okay. Suppose I have an existing stack, and this stack is, just please imagine they're green, and these are green books. Okay. So I get to assume they're green, and my construction is to add a new green book. Now, these are green, this one's green, and if I put it on top, well, this is also green. So the construction preserves greenness. And so I can this way show all my stack of books is all green. Okay, so this is the basic idea of induction, which as it was explained for natural numbers. So nothing terribly new. Okay. So the way we phrase it is to say, you know what, I'm going to prove the property everywhere. That means if every simpler piece, all right, if every simpler piece has that property, then it's also true. This is what induction is. Okay, and induction is parameterized by a relationship, this simpler than relationship. Right. So precedes, constituent of, simpler than, is below. So depending on what you're doing. Okay. So for numbers, you might think of predecessor or below. For other things, you might think part of. Like if I'm talking about expressions, right, I might want to talk about sub-expressions or sub-lists or subgroups. Okay, so the relationship is well-founded, gives us mathematical induction. Okay, and well-founded, as I tried to say a moment ago, is there is no infinite descending chain. Okay. All right. Any questions? Okay, just making sure. All right. So here's an example of how to use this to get the usual induction on natural numbers. So if we start off with the very if we want to prove a property is true about every natural number, the fact that this relationship admits induction means we can, it suffices to prove the property for every smaller piece, okay? And we're defining y to be smaller than x to mean when you add 1 to y, you can get x. Okay, that's what it means to be for y to be smaller than x. Add 1, okay? That's the relationship we have chosen. You can choose other ones if you like, okay? And there are other ones that work for different purposes, okay? And then the rest of the argument is pretty standard, right? Right here, this is true, and so we split true into x is 0 or x is greater than 0. If x is 0, that means there's only one possibility. So all x that have to be 0, so we do the 1-point rule and we simplify. Here, instead of calling this one x, we'll call it y now, call it z. And so now when you have y plus 1, z plus 1, you cancel out the plus 1s, you cancel out the sucks, okay? And you simplify further and you get this normal form of induction that we've seen, okay? If you use less than right here for natural numbers, then you might have seen this called complete induction over the natural numbers, okay? So, which is also in the book on chapter 12. Okay, ducks. So that's the one I was saying here, and we're not going to be doing any complete induction right away. I just want to let you know that it's just another theorem, and because it's just another theorem, you can use the keyword using with it. Okay, so you can prove things by induction or by the using keyword, and the using keyword is better because by induction is for this weak induction, and you might want to have access to a stronger assumption hypothesis. And so using the keyword using is a better approach. Okay, so that's why we're trying to shift you guys to the word using instead. Okay. So induction can be performed on a lot of different kind of types, as we mentioned earlier, and some of these you'll see in the rest of your classes. So you'll definitely see induction on sequences. So that's the one we're going to tackle next. It's the simplest induction after natural numbers. It's perhaps the most common one after natural numbers as well. It's very useful. The next one after that is expressions, and you'll see this one as well. It's very common in computing and software. I think you'll see it next term in 2FA3. It's very, very common. Propositional formulae can be thought of as a particular kind of expression. Trees can be thought of as a particular kind of expression. Proofs can be thought of as a particular kind of expression. And programs can be thought of as a particular kind of expression. Okay, so expressions are really they're just so flexible and so useful. And really, even finite sequences can be thought of as a particular kind of expression. Even natural numbers can be thought of as a particular kind of expression, right? Essentially, all of induction boils down, all of structural induction boils down to expressions. Okay, so today we'll start off with just finite sequences, which are a kind of expression, and we'll get to that later. Some examples of inductively defined definitions on expressions can already be found in the abridged lecture notes, if you're so inclined. Okay, ducks? Just making sure I'm not missing any questions or queries from other people. Just want to look into that. Okay. So we're starting off with sequences. The way we're going to write sequences is using square brackets. This is very popular in Haskell and many other languages use square brackets. The book is from the 90s. It's a very good book, but the book uses this notation with angle brackets. We're not going to do that. And in the system, in CalcCheck itself, we won't do either. In CalcCheck, we'll use a more abstract syntax tree approach. Okay, so lists can be formed from the empty list, or lists can be formed from a cons. Okay, so I just want to take a moment here to just clarify what this means. Let me open up a little notebook right here just to show you some examples. Is everyone following along well? Is there anyone having any trouble? Are we all good? Okay. So you can think of lists pretty much like you think of natural numbers. So there's the empty list, right? Slash eps for epsilon, right? Some mathematics people will notice we use epsilon. It's when you say for all epsilon, there's a delta in calculus, you think of epsilon as being so small. And the empty list is so empty that we denote it by this epsilon. And this is very much like 0. And then there's the non-empty list, right? Which is x cons x's, right? And this is very much like suc n, okay? All right, thanks, Damien. So another way to think of these is if you say, hey, a sequence over a type tau, B becomes, it's either empty eps or it's a value x, so a value of type tau, right? Cons a value of type sequence tau, right? And notice how this is very eerily familiar to the natural numbers are empty, or they're the successor of another natural number, right? Okay. Only thing missing is tau. Okay, so it looks very, very familiar. Nothing so strange or new. Yes. Please let me know if need to be zoomed in. Okay, so the natural numbers were either empty or one more than an empty. Okay, so I have an empty stack or I have a non-empty stack. That's what the natural numbers were. Right? It's empty or there's one more book on top of a stack. But what if I want to keep track of the titles of my books? Then I can say, all right, there's an empty stack, or I have a title of a book, and then I have the rest of the stack, right? So in sequence, I can remember the titles of my books, whereas for natural numbers, I just have a stack of books, okay? So different use cases. Do I care about how many books I have, or do I care about the list of titles in my stack of books? Okay, so that's very useful right there, okay? You're welcome. Yeah. So very, very familiar, nothing super strange. It's really just now we're adding, the only thing we're adding is now values of type tau. Almost everything from natural numbers is going to be true in lists. Maybe we'll get to it later on, but natural numbers really are lists. Natural numbers are lists that carry no information, right? The title is always, it's a book, I don't care. It's a book, I don't care. Okay, so this thing is read BB becomes. It just means the left-hand side is defined in terms of the right-hand side, and each of these is an or clause. You don't need to know this notation. I just, for people who do know it, I just wanted to show you the possibility of looking at it. So we've used it before when we talked about expressions and grammar. B becomes, but you don't really need to worry about knowing it. Okay, it's just a terse way to explain these definitions. You don't need to know it. Okay. Alrighty. Yeah. So this left-facing triangle is called cons, short for construction. Cons or construction. And so when you flip it the other way around to put things at the end of a list, this is called SNOC, which is just cons in reverse. C-O-N-S, cons in reverse. SNOC. Okay. So this is very much like natural numbers. So to get to the intuition, let's look at another one. Here's catenation. All right. So lists are sometimes also called sequences, words, depending on who you ask. So these things are also known as sequences or words. Okay, words of type tau. Okay, so when I write a book, I have a bunch of words, right? I have the empty word, or I write one word and then I write another word. Okay, so they're words or sentences, right? So it's a very, very useful type. Okay, ducks. So here's a very familiar one you may have seen. Let's look at that. Recall we had addition, right? And addition was from the natural numbers to the natural numbers to the natural numbers. Okay. Now we'll have catenation. Catenation from a sequence of some type to a sequence of some type to a sequence of some type. Okay. So very, very, very familiar. Okay. Then we said 0 plus n is equal to n, because 0 doesn't add anything. Likewise, if you have an empty list and you want to stick it beside another list, so you want to catenate, the word catenate means to stick beside or to put them together beside each other. If I want to catenate that with another list y's, this is just y's. Okay. We use plural letters instead of y. We say y's because a list is supposed to be a plural, right? There's many things in my sequence, and so I don't have one thing y. I have multiple things y's. Okay. And then we said if you have a suc m plus n, this is going to be take the suc, put it at the very front, and then do m plus n. Likewise, when you have an x cons x's and you want to stick that with y's afterwards, what you do is you first keep the first x, right? Then you stick x's with y's. Okay, so the relationship is very similar because the natural numbers are lists. Okay, so just maybe I'll write that in again. The is in some sense a kind of sequence. Okay, so that's why almost all the rules for natural numbers come up, right? So lists are like parameterized natural numbers. Okay, they have information. Okay, ducks. There's a backwards arrow somewhere. I don't see a backwards arrow. This thing is cons. This is how you make new lists. Okay, so a list is either empty or it's the cons of two pieces. So let's look at an example. Maybe that was sufficiently confusing. Okay, so I can say 3 is suc 0. That's 3. But the list A, B, C, this list is really A, cons B, cons C, cons Eps. Okay, so perhaps that was sufficiently confusing. Okay. Okay. So Nathan, the arrow is not follows from. I don't. This empty left-facing arrow is the construction for lists. Okay. So a list is either empty or the list is a cons. Okay. That's all it is. Okay. So for example, here A const with B, const with C, const with the empty list is the list having ABC. Okay, next. No worries. Please continue to ask questions. Okay. And so, for example, the definition can be thought of as mutual associativity or left identity. So a bunch of these rules for addition will translate. There's a homework on sequences already out. So let me just show you that. And because there's essentially nothing new there, just a slight adding of parameters, it hopefully won't be too difficult for everyone. Where's Kate? There's an introduction homework right there, homework 14, and then there's exercises. The homework I think is due next week. And it covers a lot of stuff we talked about. So this example we just showed a moment ago is again expanded here for you. Okay, so the homework might look a bit long, but it's a lot of exposition, right? Lots of text. Okay, so just to get you exercises, get you comfortable with these ideas. All right. Austin asks, is it necessary that we put an EPS at the very end? So Austin, this operation, cons, requires a sequence in the second argument. So it says, give me a value and then a sequence, right? So here's a value, good. Here's a value, good. Here's a value, good. But then I have to finish with a sequence. The last thing has to be a sequence, okay? Okay, so you have to, so you need to finish that way. And just in case it's vague, I'll do it again. It's like this, maybe cons C, cons EPS. Okay, so cons says I need a value and a sequence. Okay, good. So this is now a real sequence. This sequence has one thing called C. Cons says give me a value, right? Give me a value right here and a sequence. Well, that one's already a sequence, and this is a value, so this whole thing is now a sequence. But this whole thing is a sequence, and cons says give me a sequence and give me a value. And so the whole thing is now a okie dokes. Eamon asks, what does a sequence really mean? That's a good question. So what does suck 0 really mean? The meaning depends on how do you use it. We have decided to treat it as the number 3. Okay. This ugly expression, even uglier with parentheses, means the sentence ABC. Okay, so let's try another one. So if I say Jim ate it, that's a sentence, and I can say this sentence, encoded, if I want to reason about the sentence, is Jim cons ate, cons it, cons EPS. Okay, right. So I can do that, right? Use lists to reason about sentences. Okay, so that's one way I can use them for whatever task I'm interested in, right? They're just another structure. How you use it and will give it meaning. If I show you some German or some Japanese, or maybe if I show you this symbol, here's a symbol. I can't show it to you. My machine is dumb. But if I show you some Japanese, for example, or some Arabic, to you it might look like some art or some scribbles. But to someone who speaks that language, it has meaning. Okay, so the symbols don't carry meaning by themselves. It's us people with our brains that assign meaning to symbols in the way we decide to use them. Okay, so computers don't know that this is a natural number, and computers don't know that this is a sequence, right? It's us as people and our agreement that suck 0 is 3. Okay, we've attached meaning to it. It does not carry meaning by itself for the purposes of our class. For other philosophies, things change. Okay. Yes. So we can pretend these are lists or sequences of words, but you can change the interpretation and see them in a different way. And you can do that with all of mathematics. The stuff that we make up, it's not in the real world. We made it up, right? And because we made it up, we can give it meaning ourselves. This is just literally one thing, then another thing, then a third thing, right? And the structure, this cons, allows me to formally write them down, right? In a coherent, well-behaved fashion. But really, it's just 3 things. Maybe I want to treat them as multiplications. Maybe I want to say, oh, this arrow actually means times, and this EPS means 1. And then this is just multiplying 3 things by 1. That's how I will reason about it. And then catenation. What does catenation mean? Catenation will then mean multiply two products, right? One times anything is the other thing. If I have one piece, multiply the other pieces, then multiply the extra piece. Okay, so you can add on meaning to things. I kids drawing and be like, this is very superficial drawing with colors this way, and it's very abstract, and it means this, and it reflects the political nature of our world, right? So you can always add on meaning. All right, I hope that's enough. So somebody says, let's look at a real example of catenate. So let's do that. Okay. So here is A comma B, catenate C comma D, right? So what does that mean? That's just A cons B cons EPS, catenate C cons D cons EPS. Okay. The doesn't work because it works with EPS. This one says if you have a thing, move the parentheses around. Okay, so I can apply the first one, and the first one says move the parentheses from here to here. Okay, then I can do that again, and it says move the parentheses from here all the way to here. Okay, now the first rule applies, which says if you have an EPS, just throw it away. So I can now do this, throw that EPS away. Okay, and of course, parentheses we said don't matter because we're associating to the left, to the right. And so I can now say like this, and then I can go back to informal notation and say A, B, C, D. Okay. All right. So nothing too complex. All right. Great. Great. Cons puts things at the front. Snock puts things at the back. Right. So nothing too strange. So these inductively defined or recursively defined definitions are nothing really new. They're just like how you've worked with the natural numbers before. So here's an example of defining a membership relation. If I think of sequences as titles of my books, my book stack, these are titles, and I say is the title X inside the empty sequence? Clearly not. Is it inside a non-empty list? Well, if it is, then it's either the first one or it's somewhere else in my list. So I just wanted to show you an example of these things, not too difficult. We're choosing right association just to make parentheses easier. And modern languages, programming languages, also do right association for implementation reasons. We're just so that way we don't have to write parentheses. It would look much uglier if I had to write parentheses like this. It's really ugly with all the parentheses. So you pick associativity to avoid writing all the parentheses, which is something we talked about over here about why you pick parentheses, right? You pick an associativity. Otherwise, how do you read things? Using this tree or using this tree? So picking an associativity, picking a precedence, picking fixity, these things let us reduce the amount of clutter in our expressions. Okay, next. So let's get to the real reason we introduced lists. They're the next thing up from natural numbers for induction, right? So remember we said induction was to prove a property, I need to show it for the simplest case, and if it already holds, then when I add on a new piece, it continues to hold. Okay, so that's essentially induction. Nothing new there. So let me just again continue with this comparison with natural numbers. I think it may be helpful. So we say for all x of type natural numbers. For all n, this is going to be true, provided p of 0 is true, and for all n of type natural numbers, if p of suc n is going to be true, provided P of n is true. Okay, and now we're going to say for all x's, remember we use plural for lists, just to remind us it's a list, x's. For all x's of a list, we're going to show that the property is true for x's, provided the property is true for f's, right? The empty list, if it's R, if we start off with truth, that's good. And for every new value x, right, and any list x's, we can show that the construction, putting in a new element in front of a list, so putting a new element in front of a list, x's, is going to follow from P of x's. Okay, so we're saying, so it's the same scheme as before, right? To prove property holds for everything, you need to first show it holds for the simplest piece, right? The simplest piece, and then you show it holds for all constructions, right? I show it holds for all constructions, assuming it holds for the smaller parts. Okay, assuming it holds for the smaller parts over here. Okay, so again, that's all that induction is. Just you can make a thing by starting off with something small and then adding stuff on top. If that something small already satisfies P, and every time you add, all right, something on top, this addition process, this construction process preserves a P property, then at the very end, the construction will have the property P. It's like dominoes, remember? If I can hit the first domino and every domino can touch the next domino, then any domino down the line will be hit. Okay, so that's all it is, or like climbing a ladder, as we've discussed before. So the induction for this is if the empty list is true and when you add a value, yes, that's exactly what we're saying, Shrill, right? If the property is true for the empty list and the property continues to be true when you add on a new piece, then it has to be true everywhere. Okay, and just in case it's still not yet clear, the idea is if I know my constructions, my packaging, like x cons x's or suck, if I know each packaging will preserve the property P, then I just rip away the packaging. So look, let's look at it together. Here's the property, and we're going to rip off all the sucks, right? Because it's right here. It says if there's a suck, you can throw it away and just check the smaller piece. So I remove all the sucks. Eventually, I get to P0, and I know P0 is true. Okay. And down here it says to prove the property is true for an x, you just throw away all the conses until you get to the empty list, and then the empty list is true. Okay. So intuitively, just if you want to get somewhere really high up the ladder, all you have to do is be able to get on the first rung, and between any two rungs, you can reach over to the next one. That's all induction is. Okay, so just want to remind you of that. So nothing really new. Okay, excellent. Okay, and we talked about membership before. So let's look at an example for induction. This is exactly what we have on the right side of the screen. Just they're very similar, again, because the natural numbers are in some sense a kind of sequence. If you want to talk more about what that means, we can talk about it. But that statement is technically true in some reasonable sense. Okay, so let's show a theorem is true. Remember this theorem from bygone days? We said successor of n is not equal to n. Successor always makes new things. Okay, suck always makes new stuff. Okay, likewise, x cons x's is not equal to x's. Okay, cons always makes new stuff. Okay, so before, when we had no interpretation, right, we said, oh, you could think of them as numbers. So when you prove your theorems, some of your interpretations might not work anymore, and so you need to change them as you go along. Since we have quantifiers available to us now, what this statement is really saying is, if you recall from theorem 916, right? A property P is true precisely when for all x, P is true. So this is true, means for all x's and x, this is true. But wait, to show a property is true for all sequences x's, we just need to do that by induction. Okie dokes. X cannot, X is a value of type A. So X is a sequence, X is of type A, okay? X is a real value, and X is a sequence, okay? So different types. It's important to remember types, okay? I can have a word, but a word is different than a sentence, okay? A word occurs in a sentence. A sentence is made up of words, okay? So that's what tau is, okay? So if you think of sequences as word sentences, then tau is the type of words. Okay. Yes, eps is like null or nil. It's like zero. That's exactly what we're trying to show here. It's like zero. All right. Okay, next. So this theorem, what would it look like in CalcCheck? So to show that this theorem is true in CalcCheck, you can still use by induction if you like, right? You can also do using, okay? So both are available to you. I would recommend for a practice to try doing it with using, but I just want to let you know you can also just write by induction. As it stands, CalcCheck has built-in support for natural numbers and sequences. But the using mechanism is much more generic, okay? And the using mechanism, you also say, here's my subproof for this thing, my subproof for that thing. So I would recommend trying to do both ways to get comfortable. But it's the same kind of induction scheme we've done before. Here's a using, then I have a subproof for the first part and a subproof for the second part, right? And then I have a normal calculation involving a number for any's, okay? I'm thinking sequences won't be on the midterm. They're not so strange or new that it would be unfair to put them on the midterm. But I think in honoring the feedback channel, to avoid going too fast, we might not put them in, or if we do, maybe we'll put in one. But I don't think so. I don't think we'll put sequences in. I don't think we'll put sequences in. Okay. Confirmed by tomorrow, but I don't think we'll put sequences in the midterm. Okay, next. There are some examples right here that we can finally get to, some interesting examples. So before, recall we talked about less than or equal to, right? Oh, too big. Less than or equal to, right? Hashtag orders strike again. So we talked about less than or equal to for the natural numbers, right? Then we said there's implication for the Booleans. Then we said there is divisibility for the natural numbers as well. Divisibility, right? Now we're going to be talking about subsequences for sequences, right? And we're also going to be talking about is prefix, which is also for sequences. Okay, so there's different orders that you'll get to see again, right? So the reason we spoke about a generic square less than or equal to is because the properties of the generic order specialize to these other common ones that we've been telling you about, right? And assignment 13 also tries to talk more about this one and these two. Okay. So they're not that difficult. So maybe since we're running out of time, maybe we'll put them in an exercise. They're just nice examples of orders that you're probably going to see again in computing and software. Did someone ask a question? All right then. Thank you for attending this fun time with induction orders and DM3. I wish you all the best. I hope you have a fantastic Thursday. Have a terrific Thursday, and I'll see you tomorrow. All the best.